Okay, hey there. Thanks for joining me for the second lecture of solid mechanics. Today we are going to be looking at what's called strain and also stress-strain diagrams. So we'll go ahead and get started. Sometimes it's hard to realize when most of the materials that we deal with on a daily basis are fairly rigid. But anytime something's subjected to a force, it'd help if I have my pen there. Anytime something's subjected to a force, it undergoes a deformation. Now, in the last lecture, we saw how we could find internal force and use internal forces to calculate stresses. And stress was the average internal force in an object at a particular location. And because we're calculating stress as average internal force, in other words, normalizing internal force to geometry like cross-sectional area, then the measurement of stress becomes insensitive to the actual geometry of an object. So if you've got something that's very large and it's experiencing a stress, let's say, of 3 megapascals, and something that's very small that's also experiencing a stress of 3 megapascals, you know that on the atomic level, both materials are seeing the same internal force. So they're at the same state as one another. And that lets us do things like conduct material testing experiments using small pieces of material and then extrapolating the results from that out to very large objects that are made of that same material. So we can do a test on a small piece of material, determine what are called material properties, and then use that to predict how much load a much larger object made of that material is going to be able to withstand, or be able to determine what are the required dimensions of something made of that material that's going to be taking a much higher load. We do the same thing with deformation. So we normalize deformations based on the original unloaded geometry of an object. And doing that normalization, we get what is called strain. So as deformation is to force, strain is to stress. They're sort of, they're related to one another. Now, we were introduced, or we learned about the two fundamental types of stress in the last lecture: normal stress and shear stress. So let's look at how strain comes into play for each of those stresses. So I'm just going to actually flip to a new page to give myself more real estate here. So for normal stress, a normal stress, and we had a normal stress being represented by the Greek letter sigma. Normal stress is related to normal strain. And we give normal strain the Greek letter epsilon. Okay, so just like forces to deformation, stresses to strain, and a normal stress is related to a normal strain. So we know that normal stresses can be tensile or compressive. So let's just look at a case of a tensile normal stress, or a situation of something that's under a tensile normal stress. So let's just say this is a flat plate. And it's going to be under load F here, and it has like an original unloaded length, we'll say, of L naught there, and an original unloaded width of W naught, and then into the plane of the board, it would also have some original unloaded thickness, T subscript naught. So I'll just make a note there, thickness into, I'm saying board like I'm lecturing on a whiteboard, into the plane of the screen, thickness into screen. Okay. Now, we know, for not all materials, but most materials, as they get longer, and all materials will if they're subjected to a tensile force, they get a little bit longer, but most materials also get a little bit thinner too. There are some materials that do the opposite. They actually get a little bit thicker as they get longer for this sort of situation, but those are, pretty rare. So there's the sort of deformed geometry, and our equation for normal stress, sigma equals n divided by a, where n is the internal normal force, which in this case is of course equal to force F, that's being applied if you do your section cut and look at the free body diagram. N is equal to F. But the point here is that we're normalizing the internal normal force to cross-sectional area. And the cross-sectional area here that we're using, this is the cross-sectional area of the object in the unloaded state. Okay, so area A is AO, A subscript O, which is unloaded cross-sectional. There we go, cross-sectional area. Okay, and that's always the case here, and this gives us what's called the engineering stress. Okay, so this gives the engineering stress. Okay, and there is something called true stress as well, and we'll talk about that a bit when we talk about stress-strain diagrams in a bit. But for the purposes of this course, whenever we calculate stress, it's always the internal normal force divided by the unloaded cross-sectional area. And in fact, all of our calculations are always with respect to unloaded geometry of objects. Okay, so normalized force, internal force by cross-sectional area. For strain, we do the exact same thing. So if the deformation that this object experiences under load F, let's say it elongates by a total of delta L, then on the top here, we would have half of that. So this is 1/2 of delta L, and on the bottom 1/2 of delta L as well. And then there's going to be some contraction in width. So this, let's see, where are we going to show that? Maybe right here. This distance here is going to be 1/2 of delta W. Okay, and similarly, we get a contraction in thickness into the plane of the page, delta T. So strain, epsilon, is equal to the change in length that the object experiences divided by the original length. Okay, and if we look at units here, whenever we show units, put the equal sign in square brackets there. We've got length per length, so we've got meters per meter, or inches per inch if we're dealing with US units. And even though those units cancel out, you should show the units for strain, because it's also common for people to present strain in units of percent, which would be multiplied by 100 compared to units of meters per meter or inches per inch. So if a value of strain is shown and there's no units, it's not clear whether it's in actual units of strain, length per unit length, or in percent, length per length multiplied by 100. So always show your units of strain. This is actually called longitudinal strain here. And if you just see epsilon without a subscript below it, it's always implied that you're talking about longitudinal strain. So strain that is in the direction of the length of an object. So we can also measure a strain that would be lateral, so due to the change in width of the object. So here the lateral strain is the change in width divided by the original width, which will be identical to the ratio of change in thickness over original thickness. So delta T over T naught. So those two will be identical, and most often the ratio of delta W to W naught, or delta T to T naught, is smaller than delta L to L naught. And the relationship between longitudinal strain and lateral strain, so how much something contracts laterally when it elongates longitudinally, that's a property of the particular material that you're dealing with, and that's a ratio and a material property called Poisson's ratio, and that is given by the equation Greek letter nu equals the negative of the lateral strain divided by the longitudinal strain. So, and this is a material property, right? Okay, and that is Poisson's ratio. There we go. Okay, so that's normal strain for you there. So let's just do a quick example with let's actually introduce shear strain first, and then we'll do a quick example with normal strain. Okay, so just like we said, normal stress is related to normal strain. We have shear stress, and that has the variable tau, is related to shear strain, and that gets the Greek letter gamma. Okay. Now, if we look at something deforming under shear stress, we can draw a picture of something that's deforming under a state of shear stress. So let's say we have a box here that's fixed to a base, and we apply a horizontal force like this. We know what's going to happen in terms of geometry here. If the base is fixed, the object's going to sort of skew over like this. And the way that shear strain is measured and defined is looking actually at the change in angle of a set of axes that was originally at 90 degrees on the unloaded object, and measuring how that set of axes changes when the load is applied. So if we take our sort of before and after case here, so here's the picture of the unloaded object here, and then if we look at the loaded object below, there we go. Okay, here's our loaded object. So to measure shear strain, what we do is we take a set of axes here with 90 degrees, and then we measure the new angle between those axes when the object's being deformed. So that's under the influence of load F here, and that angle is theta prime. And then shear strain gamma is defined as the difference between the original angle, right, theta, subtract theta prime. And the original angle is always 90 degrees, so we have pi over 2 here minus theta prime. So that's our equation for gamma. Now I realize I didn't put the equations here in boxes back for normal strain, so I'll do that just so that the notes are nice and neat here, and you can clearly see where the equations are. That's always nice. Okay, now because we're using pi over 2 here, the units of shear strain are always in radians. Okay, important to realize that. So let's do a quick example then with normal strain. This is really basic, arguably not even necessary, but it's it's always nice to have numbers attached to things and just show the calculations. So let's say we have a flat stainless steel plate, 304 stainless steel here, and the original length of this is let's say 2 meters long, and we've got cross section shown here that has dimensions of thickness, let's say 5 millimeters, and height or width of the plate is 50 millimeters. Here we go, 50 millimeters. Okay, so stainless 304 plate. Okay, so under load, we'll say that plate extends by 5 millimeters. Okay. What we want to know is A, what's the strain, and B, what's the change in width the plate will experience. Okay. So the first thing that we'll do here, we'll do part A first. The first thing that we'll do is look at strain. So strain, if it's not stated otherwise, again, just strain stated plainly like that, you understand that it's meaning longitudinal strain. So we have epsilon equals the change in length over the original length, and we can just pop that in. So if it extends by 5 millimeters, we've got 5 up there, and let's make that times 10 to the negative 3 to change it to meters, and then we've got 2 meters on the bottom. So units of meters per meter, that gives us 0.0025, and showing units meters per meter. Okay, easy. Okay, and then for part B here. All right, so part B, we want the change in width. So we only have information about how the length changes, but we know that the amount that something elongates and the amount that it changes or contracts in the lateral dimension will be related through the material property called Poisson's ratio. So the first thing that we need to look up is what the Poisson's ratio of 304 stainless steel is, and you can look that up in the material properties table that's located in the back of the textbook. So the Poisson's ratio for 304 is 0.27 when you look it up. So using that, we know that the Poisson's ratio is equal to the negative of the lateral strain over the longitudinal strain, and lateral strain is change in width over original width, and longitudinal strain is change in length over original length. So now we can just pop in all our numbers and solve this here. So we've got, we'll just flip to a new page. 0.27 is equal to our negative, wait a second here, yep, negative of delta W divided by W naught, and that was 50 millimeters. So we'll take this 50 times 10 to the minus 3 divided by change in length over original length. So we've got 5 times 10 to the minus 3, 5 millimeters divided by 2 meters. Okay, and then we've got delta W comes out of that as being minus 0.034 times 10 to the negative 3 meters, okay, or minus 0.034 millimeters, okay. Negative sign there to indicate that the width is contracting. Okay, so that's all there is for the basics, really, of calculating strain. So let's turn our attention to stress strain diagrams and talk about stress strain diagrams a little bit. So we've got stress strain diagrams, abbreviated as stress strain diagrams. Okay, so these are normal stress, normal strain diagrams we'll cover here. Okay, so the first thing we're going to look at is what stress strain diagrams look like for ductile metals. So most of the metals that are used in engineering are what would be classified as ductile metals. And ductile just means the property of being able to undergo significant deformation before failure. And that's the opposite of brittle. So a brittle material is one that can't deform significantly before failing, whereas a ductile material can deform significantly before failing. So most of the engineering materials, your steels, aluminum alloys, titaniums, these are all ductile metals, and they all share similar characteristics in terms of the response of stress to strain when you look at plotting those two things against each other. So what we're going to imagine doing is an experiment here where we take a small piece of material like this, and we subject it to an increasing tensile load F. And while that load is increasing, we constantly measure normal stress, which would be the internal normal force divided by the original unloaded cross-sectional area, which of course equals F divided by A. And at the same time, we also calculate strain. So that's the change in length that the material undergoes divided by its original length. And what we want to do is plot those two measures on an XY scatter plot against each other. So we have always put strain on the x-axis and stress on the y-axis. And actually, I'm just going to elongate this axis a little bit so it's more of a square here. Okay, there we go. So we have strain over there. Now, all ductile metals most ductile metals have very similar stress-strain curves when you plot stress against strain and do an experiment like this. And this is just a tensile testing experiment. So starting from a condition of 0 stress, 0 strain. So this is when our applied force F is equal to 0, and we have no deformation, no force applied, no deformation. As force begins to increase, there is a linear relationship between stress and strain that develops. And that linear relationship continues until the curve starts to decrease in slope. There we go, decrease in slope. And actually, we'll draw the whole curve, and then we'll break it into parts and talk about it. So then it stays flat for a small period of time, or close to flat, and then the curve will start to increase again, reach some sort of maximum point, and then drop down to result in the point of fracture here when the actual material breaks. Okay, so there's our point of fracture. So you can break a stress-strain curve here into 4 sort of primary regions. So we have the region from 0 load up to the end of linearity, right? We'll call that region 1. Then we have the region where the curve sort of has a flattish portion, so that's region 2. And then up to the maximum stress on the curve, so that's region 3, and then we have region 4 here, from maximum to failure. So what we're going to do is we're just going to talk about each of those regions and the characteristics that we see there with each of them. So I'm just going to copy this, and we'll take it and we'll paste it on a new page. Okay, so here we go, paste that there. Okay, so let's talk about region number 1. Region 1. Okay, so this region, because stress and strain are linearly related to one another, this is called the elastic region. Elastic region. So just like a spring equation, F equals kx, where force and deformation are linearly related through the spring constant, here we have stress and strain being linearly related through what's called the modulus of elasticity. Okay, so we've got stress equals modulus of elasticity times strain. Okay, so this is the modulus of elasticity. Okay, here we go. And that is the slope here of the stress-strain curve, big E modulus of elasticity. And the point at which linearity stops on this curve is called the yield point, and we represent that by the yield stress sigma subscript y. Okay, so the elastic region ends at the yield stress sigma subscript y. Okay. Now, within the elastic region, materials behave sort of, the same way as you think a rubber band behaves. You stretch it out, and when you release that extension force, the rubber band returns to its original unloaded length, and that's exactly what materials do in the elastic region. So you can stretch them, and they return to their unloaded length, stretch them again, return to their unloaded length. So deformations are reversible in this region. Okay, so if I show a loading line in blue here, so let's say we go from 0 and we load the material up to, let's say, this point. There's our loading line. And then I do unloading in red. The unloading line follows exactly on top of the loading line, and same path is taken. Okay, so deformations below sigma y are reversible. Okay. All right, so let's go to region 2 now. So paste that back in there. Okay. Region number 2. Region 2. Okay, region number 2 is called the yield region. Okay, so at this point here, we are above the material's yield stress sigma y. And after you exceed the yield stress, the stress strain curve really levels out. And what this physically means is that to keep extending the material requires less and less input force per unit extension. Okay, and some curves really are, for some materials, like for irregular mild structural steel, the curve actually decreases in slope a little bit after the yield stress, or has a slight region of negative slope, and then really is completely flat. And a completely flat curve means that the material is continuously getting longer with no additional applied load, which is kind of interesting. People don't think of rigid materials like steel as behaving that way, but we'll see that really is the case in the labs that we do for the course. So if we look at the loading line here again in blue, let's say we're starting from 0 and we load up and we go past the yield region, or the yield stress, into the yield region somewhere, let's say there, and then we unload. The key thing about exceeding the yield stress, excuse me, is if you exceed the yield stress, when you unload a material, it will not return to its original unloaded dimensions. So our unloading line would actually be parallel to the material's modulus of elasticity. So here we go. It would go straight down like this and stop right there on the curve. So we've got loading line in blue, unloading line in red. This portion of the curve had slope E, big E, modulus of elasticity. This portion of the curve also has slope E, that same E, modulus of elasticity. And this distance here, right, from the origin to the point where the stress strain curve crosses the x-axis on unloading, that represents the deformation that wasn't recovered when the load was removed. So down at 0 on the stress axis, right, we don't have any load being applied to the material at all, but we still have a strain that is existing. So this is what's referred to as a permanent set. Permanent set. Right, so we've caused permanent deformation. Okay, so let's make a note of that. If our stress is greater than our yield stress sigma y. Deformation causes permanent length change. Okay, permanent length change that's not recovered under applied load. All right, so that's region number 2. So let's talk about region number 3 now. Here we go. Okay, region number 3. Region number 3 is referred to as the strain hardening region. Region 3. This is called the strain hardening region. Now, what is special about this region is really only appreciated when you load a material into the strain hardening region, unload it, and then reload the material. So let's look at doing that. So we start off down at 0 stress, 0 strain, load a piece of material up following the blue line into the strain hardening region, let's say to this point there, so this is our loading line all the way up to there, and then we unload the material. So we've got modulus of elasticity, big E over here. When we unload the material, again, the unloading curve is linear and has a slope of E, the material's modulus of elasticity. So I'll try and draw it roughly parallel here. So there we go. This curve, actually that covered up my arrow a bit, that curve has slope of E. Now the material's original yield stress was here, sigma subscript y. Strain hardening the strain hardening region is exploited all the time for material processing. And when a material undergoes strain hardening, it's purposely taken up into the strain hardening region of the curve, and that is for the purpose of increasing the material's yield strength or its yield stress. Yield stress, yield strength, synonymous terms. So when you reload this material after it's being unloaded, so now we're starting from there, right? The material will behave linearly, and then at the point where we had our original yield stress, the material will remain linear and in its elastic region until it rejoins where it left off on the loading curve. So then it will continue here. So by taking the material into the strain hardening region and unloading it, we've effectively increased the material's yield stress or yield strength to sigma y prime. And this doesn't need to happen just through tension, for example. You could have this done through compression, which is most often the case. So if you think of if you get really old-timey and think about a blacksmith hammering on a sword, that's sort of strain hardening, continually deforming the material, taking it above its yield strength, causing permanent deformation. That's strain hardening. So the same process is done to steels that are used for kitchen knives. And if you think about aluminum being rolled down in between rollers and squished into progressively thinner and thinner form factors, that's strain hardening as well. Okay, so strain hardening region. I should say that for the yield stress here, the original yield stress, if we just extend our line up here, any deformations that occur under the yield stress are referred to as elastic, and any extensions or deformations that occur to the right of that, exceeding the yield stress, are referred to as what's called plastic deformation. So here we go, plastic So plastic deformations or plastic regions of the stress strain curve would be regions 1, 2, or 2, 3, and 4 all together. Okay, so strain hardening, so this is used to increase materials yield stress or strength sigma y, and then we'll just make a note, does not change modulus of elasticity E. Okay. There we go. So let's do region number 4 now. Paste that. There we go. All right. So region number 4. Region number 4 is referred to as the necking region. So region 4. This is the necking region. Okay, so up until the end of region 3, and this maximum point here that marks the end of region 3 is what's referred to as the material's ultimate stress or ultimate strength. Okay, so this is the ultimate stress or ultimate strength. Up until the ultimate strength during loading, so the whole while we were through the elastic region, through the yield region, through the strain hardening region. Here was the yield stress way back there. The object sort of was originally rectangular, right, being loaded, and we know that as the object extends, or as we go up on the stress strain curve, the object is elongating and becoming a little bit thinner as well. So we've got something like this. So here's, and this is a pretty dramatic difference in width and length that I've drawn. So this is what the object looked like in sort of region 1 here, and this is maybe what it looked like at the end of region 3. So at end of 3, right? At the start of the necking region, we have deformation that becomes very concentrated at a single location within the sample and creates what is called a necking region. So I'm just going to actually move this over a bit so I can draw next to it. Okay, there we go. And we'll just take this little portion here and move it down here. Okay, perfect. So in region 3, we have the object going from what we had here to something that looks more like this, where a very focal area of deformation will occur, where all the deformation then is being concentrated and focused in this necking region. Oops, meaning to put the force in there. Okay, so this is the necking region. Perfect. And that's where our fracture will eventually form, right in the necking region there. So not too much to be said about the necking region, other than the fact that the geometry, overall geometry of the object stays relatively similar up to the start of the necking region in terms of the object being rectangular and remaining rectangular. And then in the necking region, you really do get a deviation from that. So thinking back to our sort of earlier point that for stress here, we always measure or always calculate stress as normal force divided by, or we always calculate normal stress as normal force divided by original cross-sectional area or unloaded cross-sectional area. So this is unloaded area. Okay. And our strain is change in length divided by original length. Because we use the original unloaded cross-sectional area here, the stress-strain curve that's produced is called an engineering stress-strain curve. And because the object stays, fairly rectangular moving through and doesn't significantly change in cross-section too much, if you were to instead calculate stress by dividing, instead of by the original unloaded area, by the instantaneous cross-sectional area at every moment, you can see that when you get into the necking region and get a very focal deformation, your area actually goes down significantly. And that reduction in area actually causes the stress in the necking region to increase if you plot what's called a true stress-strain curve as opposed to an engineering stress-strain curve. And true stress-strain curves are more things that are used by material scientists. So the true stress-strain curve would sort of have a curve that looked more like this, where fracture is up here. Okay, and what this curve represents, so I'll just label that true stress-strain curve, whereas this one here is the engineering stress-strain curve. The true stress-strain curve shows that even though the object is on its road to failure, the actual material, the material itself is still becoming stronger in this location. But from an engineering standpoint, that doesn't matter to us, because after we surpass the ultimate stress, the actual object or structure that is built out of this can take less and less load. So it takes less and less load to continually deform, and that means that failure is imminent. So we won't look at true stress-strain curves or anything else to do with those in this course, but just be aware that those do exist and are used. But in engineering practice, we always calculate stress based on unloaded cross-sectional area, and that gives us what's called engineering stress and an engineering stress-strain curve as a result. Okay, so let's also just briefly look at what a stress-strain curve would look like for a brittle material as opposed to a ductile material. So if we go back here, and we'll just paste our previous curve in here again, and maybe we'll just do a little bit of resizing there. So this was for a stress-strain curve for a ductile metal. Okay, and again, all ductile metals share sort of similarly shaped curves, not all, most. So now let's draw the stress-strain curve for a brittle material. So this one's pretty pretty basic in terms of regions compared to the previous one. So we've got stress and strain. So this is going to be the stress strain curve for brittle material. Okay. Again, we start at 0 stress, 0 strain. Just like a ductile metal or a curve for ductile metals, the line is linear at the start. There we go. So we've got a linear relationship to stress and strain, and this more or less continues until fracture occurs. Fracture. Okay, there we go. No yield stress for brittle material, but we do have an ultimate stress, and there's the material's modulus of elasticity E. So here in comparison was our ultimate stress, our yield stress, sigma y, and here's our modulus of elasticity E there. So you've got your ductile and brittle stress strain curves right next to one another. Okay, the last thing that we'll look at today is what the shear stress, shear strain curve looks like for a ductile metal. So we can, just like we can plot a normal stress strain curve, you can plot a shear stress strain curve. Experiment's a little bit more difficult to do, but it can still be done. So this is shear stress strain curve for diagram for ductile metal. There we go. Okay, so we take X and Y axes like this, and shear stress tau goes on the y-axis, shear strain gamma goes on the x-axis. So if we loaded something from 0 stress, 0 strain, then the curve would again be linear, okay? And the slope of the curve here, where the curve is linear, is referred to as the modulus of rigidity, and that's given the symbol G. And that exists until the curve deviates from linearity, and after linearity, what happens with the shear stress strain curve is it just kind of rolls over like this to the point of fracture here. So this point here where linearity stops, that is the shear yield stress. So this is the shear yield stress or strength. And this is G is the modulus of rigidity. There we go. Modulus of rigidity there. So not too much else to say about a shear stress strain curve other than same thing applies where you've got the curve divided into your elastic regions where the deformations are reversible. So as long as you don't exceed that shear yield strength, when the load is removed, the object will return to its unloaded geometry. And you've got the plastic region where if you exceed the shear yield strength, then deformations are not reversible any longer. Now, just one other point for the ductile metals that I forget to mention is that these curves here, we generated this curve for our theoretical for our thought experiment of a piece of material being being stretched in tension. The curves for ductile metals look the same for tension or compression, and none of the properties change in values either. So the yield stress and the ultimate stress and the modulus of elasticity for things like steel, aluminum, titanium, same in tension and compression. Okay, so curve and properties. Okay, properties, same for tension and compression. Okay, there we go. So that's an important point to note, and you can see that if you go to the textbook and look at the material property tables, that the properties for those materials will be the same in tension and compression. Okay, so that's the end of lecture 2. I will see you again for lecture 3.